All right, welcome to This Explainer. Today, we're diving into something that is honestly a massive game changer in cybersecurity, the dawn of adaptive, AI-driven computer worms. Now, for years, we've kind of thought of computer worms as pre-programmed missiles, right? They launch with a specific payload and take down targets with a known vulnerability. We've seen the sheer damage they can do. I mean, think of WannaCry or NotPetya, causing literally billions in damages. But what happens when that missile can actually think for itself? What happens when it can change its strategy on the fly and learn from its own mistakes? Well, that's exactly what researchers have just demonstrated, and it is fascinating, if also a little terrifying. So, here is our roadmap for today. We'll start with the adaptive AI threat, break down the anatomy of this new worm, peek inside its reasoning graph, check out the actual lab experiment, and finally, discuss the destabilizing cyber asymmetry this creates. Let's jump into Section 1. The adaptive AI threat, a new paradigm. To really appreciate what's going on here, we have to recognize how the threat landscape is fundamentally shifting beneath our feet. Think about it like this. Traditional worms, they're basically just lockpicks designed for one specific keyhole. They are precompiled and rely on a fixed exploit. So if you patch that specific vulnerability, if you just change the lock, the worm is stopped cold. It's totally rigid. But AI-driven worms, they operate on generated logic. They are way more like master thieves who learn how to bypass any lock right there on the fly. They synthesize target-specific attack strategies at runtime based on the reconnaissance they do once they're already inside a network. If one window is locked, no problem. They just revise their strategy and try the back door. The crucial takeaway here is that we aren't just dealing with static lines of code anymore. We are dealing with a reasoning entity. The researchers are calling this an autonomous generative adversary, and it propagates entirely without human operators. It's not just running a dumb script, it's actively reasoning about the targets it encounters. It's adapting to the error messages it gets back, and it's synthesizing brand new attack logic in real time. Moving right along to Section 2, Anatomy of the Worm, Stealing Compute to Survive. Because to actually pull this off, the worm needs serious brain power. But it can't just ping commercial AI APIs like OpenAI or Google because those can be easily monitored or shut down by the vendor. So it has to bring its own brain. And it does this by literally acting like a parasite. It hijacks computing power from infected hosts, specifically those with powerful GPUs, to run its own open-weight large language model locally. When the worm finds a machine with a beefy GPU, it drops a copy of the LLM right there. That machine then transforms into a reasoning node. It uses that stolen compute to serve reasoning to other, smaller devices it infects on the network, like an IoT printer or a basic workstation, continually extending its reach. Because the worm distributes its reasoning across these infected machines, there's no single point of control whose removal halts the whole thing. It's entirely local. That means those centralized safety controls we usually rely on, like a cloud provider noticing weird activity and cutting off API access, they are structurally irrelevant here. If defenders take down one compromised GPU server, the swarm just shrugs and redirects its queries to another one it's already captured. It is an incredibly resilient, distributed network of decentralized intelligence. All right, Section 3, Inside the Reasoning Graph, the brain of the swarm. Let's actually map out how this creates a harness to direct the attacks. You see, smaller open-weight models aren't quite as smart as the massive cloud models. If you just let them loose, they get confused really easily. They need a lot of structure. So, to solve this, the attack lifecycle is broken down into 3 precise sequential phases: discovery, exploitation, and replication. First, it identifies reachable hosts and services. Then, it exploits an exposed service to gain control. And finally, it stages its own code to launch an independent replica. By forcing the AI to focus on just one of these phases at a time, the system prevents the LLM from getting ahead of itself, like trying to escalate privileges before it's even established a basic foothold on the network. And here is where it gets really clever. This reasoning graph acts like a strict internal monologue for the AI, giving it laser focus within those phases. Instead of just throwing one huge prompt at the AI, the graph splits the thinking up. A plan node proposes a strategy. A judge node reviews that strategy against past failures so it doesn't repeat a mistake. An action node executes a specific tool. A summary node extracts the hard facts from all that messy terminal output. And finally, a progress node decides if it should keep digging or pivot to a new vulnerability. It's a highly disciplined loop, keeping the AI totally on track. Okay, Section 4, the lab experiment. Testing the monster. Because, theory is great,
But what happens when you actually build this thing and let it loose?
The researchers built a safely contained, hypervisor-enforced virtual environment called Fake Corp, and they released this threat into a simulated network of 33 completely different hosts. This wasn't some basic setup. It had varying versions of Linux, Windows servers, and IoT devices. They seeded the network with specific known vulnerabilities, along with broader, real-world weaknesses like poor security hygiene, misconfigurations, and standard default credentials.
If we trace the flow of attrition across 15 independent test runs, following the AI from initial vulnerability detection into the exploitation phase and finally self-replication, you'll notice a massive squeeze right in the middle. That visual bottleneck, that is the absolute core finding of the whole experiment. Just look at these success rates. The AI was amazing at spotting vulnerabilities, nailing it 82% of the time. And if it actually got in, it replicated successfully 88% of the time. But that middle step, the actual act of breaking in and exploiting the system, dropped all the way down to a 44% success rate. So what's causing that massive bottleneck? Well, while the strategic reasoning was surprisingly sound, the smaller open-weight model really struggled with the mechanical precision you need to write perfect exploit code. Actually, 66% of those failures were simply payload execution errors. The AI would correctly identify something like a SQL injection vulnerability, but then it'd make a tiny syntax mistake, like a mismatched quote in the code. It also fumbled when trying to parse deeply nested HTML, and it found Windows PowerShell environments to be pretty tricky compared to standard Linux.
But here's the crazy part. Even with that 44% bottleneck, the swarm still wins in the end. Because it works in parallel, it just relentlessly hammers away at those individual errors. If one replica fails because of a typo in the code, another replica on a different machine will try a completely fresh reasoning trajectory against that exact same target until it finally breaks through. Over just 7 days of autonomous propagation, the swarm spread outwards, compromising hosts all the way up to a 5th generation. They even saw the swarm sharing harvested passwords across the network to unlock entirely new machines.
Which brings us to our final section, number 5. A destabilizing cyber asymmetry, the zero-cost threat. Let's zoom out for a second and look at the macro impact this has on the world, because what they proved in that lab represents a fundamental shift in the economics of cyber warfare.
The marginal cost for attackers literally drops to zero. Zero! Because the AI worm steals the compute it needs to survive and reason from the victims themselves, the attacker pays absolutely nothing to scale the infection. They launch it once, and the worm just harvests the GPUs of whoever it infects to fuel its own brain power as it spreads. This completely flips the historical trade-off of cyber attacks on its head. In the past, you either had expert human hackers doing highly tailored but incredibly slow attacks, or you had traditional worms that were infinitely scalable but very rigid and dumb. Well, AI worms are both. They are infinitely scalable and highly adaptable to specific targets. In fact, the test showed this worm could instantly ingest public advisories for brand new one-day vulnerabilities and weaponize them immediately, way before an IT department could ever patch them. This means our defenses absolutely must evolve towards strict zero-trust architectures and network isolation. As the researchers put it, autonomous, generative cyber offense has crossed from theoretical risk to demonstrated capability. They published this study, carefully withholding the exact code, of course, because we can no longer pretend this is just science fiction. We have to understand it to defend against it. So I'll leave you with this question to chew on. How does society defend against an adversary whose marginal cost of attack is exactly zero? When the attacker has infinite patience, infinite scale, and pays absolutely nothing for the computing power it takes to break into your systems, how do we adapt? It's a question every organization is going to need to answer, and very soon. Thanks for joining me on this explainer, and seriously, keep those networks isolated.